Okay, doing our problems from the worksheet for chapter 2, chapters 1 and 2. The first one, the concept here is add these, divide and add and get the correct significant figures or significant digits. So the concept is significant figures. So I am going to try to add a pin here as we're going so I have some more colors. I am going to now go through and do the problem to determine how many significant figures I have. And the first thing I have is I tell you to do the division first. I'm giving you instructions here in doing the problem. Obviously on the test you wouldn't have instructions, but I'm trying to get you to think about what you need to do. And this time I said do the division first. Why? Well, when you're doing math, you have the orders of operation. You do the powers first, then multiplication, division, and then you finally do addition or subtraction. So I think what my son learned was my dear Aunt Edna or something like that. I don't know. I never learned any of those mnemonics. They didn't stick with me. So I'm going to do the division first. So if I'm going to do that, I need to use the rule for significant digits involving multiplication and division. And that rule is the number of significant digits in the answer is equal to the smaller of the number of significant digits that I started with. You know, I am kind of worried, yeah. So we started with this number. How many significant digits? Well, remember the rules. If it's not 0, it's always significant. So right away, we can say significant, 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 significant. So I just underlined 6 of them. Our second rule is if it's a 0 that's between significant digits, it's significant. So this is also significant. All 7 are significant, so I have 7. Now the second number, 0.6210, again, all numbers that are not zeros are significant. So I have 3. And then all zeros between significance, well, I don't have any zeros between significance. The next rule is a trailing 0 after a decimal. So here's a trailing 0 after a decimal is significant. Leading 0 after a decimal is not significant, or before a decimal, so we have 4 there. So then I say, which number is smaller, 7 or 4? Well, obviously 4 is. So the result of the problem is going to have 4 significant digits. And then I just have to do the math. If I do the math, doing first the division, I get 1648.231. Actually 232 if you want to round off correctly. Now that 232 is all insignificant, but I keep it until I'm at the end of the problem because you don't want to throw away information before you get to the end of the problem. So now going to the addition, we have a different rule for addition. And so here I ask for the rule for addition and subtraction. When adding or subtracting, the least significant digit is in the answer is the greater of the least significant digits we started with. So what is the least significant digit? For each number, you look at the rightmost digit that's significant. So in 2.54, the rightmost number was 4, and so that's in the hundredths place. Hundredths. Or if you prefer, you can put 10 to the minus 2. Now in this number that we got from division, it had 4 significant digits, so the least significant digit is this 8. That's the 4th digit, right? And so that's in what we call the units place, or if you prefer, 10 to the 0. Now, using our rule, the greater of those, well, 10 to the 0 is bigger than 10 to the minus 2, so it's going to, the answer is good to the units place. So now if I add those numbers up, if I add them up, I get 1650.772. But it's only good to the units, so that rounds up to 1651. So that's what the correct answer is to this problem. Notice I didn't apply my significant digits until that last step. If I had applied them early, then, well, I may or may not have rounded properly. I actually didn't pay attention to that. I probably should have chosen like 2.34. And then if I used 2.34, it would have rounded correctly. Anyway, so that's a practice problem using significant digits. And you are definitely going to have in the exam one problem where you have to do something like this and get the right number of significant digits. Now for our second problem, oh boy, okay, there it is. For our second problem, we have two cars that are racing. Car A has a top speed of 55 miles an hour. Doesn't go very fast. While car B has a top speed of 273 miles an hour, that, my friends, is fast. And it can go from 0 to 60 miles per hour in 2.2 seconds. Now, the first thing I'm going to note here is how many significant digits do I have? There are 2 significant digits. There are 3 significant digits. There are 2 significant digits there. 60 is ambiguous. 60 could be 1 because that 0 is not between significant digits. Or it could be 2 if I actually know it's significant. So we need a way to indicate that. One way of indicating that that 0 is significant is to put a decimal point. 60 point means that 0 is significant. Or I can put a bar over it. So 60 with a bar over the 0, that makes the 0 significant. In either case, I intended for this to have 2 significant digits. For all the numbers except for the 273. Now, I have here a little funny idea of a fair race. I want to have a fair race between the two, kind of like, a man races a horse. They can choose the distances right, so it's a fair race. Either one could win. And so in this case, what I'm going to do is I'm going to say, let's allow the 55 mile an hour max car A, to have a running start. So he's going to come by the start line at maximum speed. And car B, she's going to start off at rest at the moment that car A passes the start line, and then she's going to accelerate. And I want to choose the distance where they should meet. And if I make that my distance, then it should be a tie. If somebody wins, then yeah, it was a fair win. Now, the concept involved. Well, it's not significant figures. We're going to have significant figures, but that's not the concept this time. What is the concept? Well, we have things like speed or velocity and acceleration, and that we call kinematics. And if it's a kinematics problem, then kinematics, I'm going to need to use the kinematic equations to solve it. So I'm going to start off right now by writing the kinematic equations. We have x equals x0 plus v0t plus 1/2 at squared. That's your most commonly used kinematic equation. We also have v equals v0 plus at. The zeros mean at time 0 or initial. We also have v average is equal to v initial plus v final over 2. That's really rarely used. And then we have 2a x final minus x initial is equal to v final squared minus v initial squared. So those are our kinematic equations. Of these equations, this one here is the one we use the vast majority of the time. But this one here is useful if we're only talking about speed, acceleration, time, and we don't care about position. This one here is useful in the case where we're talking about speed, position, and acceleration, but we don't have time and we don't care about time. So those are the equations we're going to use. Now, looking at our physics ideas. So this is where the real physics comes in. I wrote down the real physics for you. The cars will tie if x sub a, that means the position of car A, parentheses TF, that means at the time final. So at the time the race ends, if the position of car A is the same as, equal to, x sub b, the position of car B, at time t final at the same time. So at the time when the two cars are at the same location, that's the time I want. That's going to be the distance I want when I calculate distance from that time for the race to end. So the first thing to make sure I understand what's going on is to draw a qualitative graph. Qualitative means without numbers. So I'm going to draw a qualitative graph for the race. So I'm going to have time in units of seconds and position in units of meters. And then I need to have a title that's meaningful. So I'm just going to say car race. That's meaningful. That tells me exactly what's going on. And notice I don't have any numbers here. I just have the designations. And so I'm going to start by drawing my car A. Car A is traveling at a constant speed. I guess I should have done this first. On a graph, well, we know speed. Oh, that's too thick. But I can modify that. There we go. Speed, by definition, is change in position over change in time. But if I'm doing a graph with position on the vertical axis and time on the horizontal, that means change in position over change in time is rise over run, otherwise known as slope. So the speed will be the slope of a straight line. So I'm drawing a graph with a line that's straight starting at the origin, and that's going to be car A's graph of its position as a function of time. Now, I know this doesn't make sense, but I'm changing the color of this because I don't want any confusion. And of course, I missed the SP because, hey, you don't want to be perfect now, do you? There we go. Now for car B, let's change this color blue. I don't like that shade of blue. More colors. Really? Give me some better shades. Well, we'll stick with that color, I guess. So for car B, it starts out with a slope of 0 because it starts at rest. But then it's going to speed up, so it's going to be going like this. So that's what car B is doing. And so now I want to find the time and distance where the two are equal. So there's vertical line. Get it so it's crossing the right spot. And there's the time when the race should end. And the distance when the race should end corresponds to that time. There's the distance for when the race should end. So this is a graph of how the cars are moving and how I'm going to determine when the race is over. So I've drawn a qualitative graph of position versus time for the two cars during the race. Now I'm going to focus on car B. And car B, we have 0 to 60 miles per hour. So I need to convert 60 miles per hour into my SI units of meters per second. So 60 miles per hour, the per just means divided by. And now I need a conversion factor. So my conversion factor, we know that 1 mile is equal to 1,609 meters. We also know that 1 hour is equal to 60 minutes and 1 minute is equal to 60 seconds. So if I put those two together, 1 hour is equal to 60 times 60 is 3,600 seconds. Now, conversion factors always need to be factors that equal 1. So if I take 1609 meters and divide by 1 mile, that's equal to 1. So there's my conversion factor. Now, how did I know which one goes on top? I had miles on top in miles per hour, so I need miles on bottom so that the units will cancel. And then I have meters on top, and so just putting my numbers there. And then for my time conversion factor, I have hours on bottom, so I need hours on top, so it'll cancel. Seconds on bottom, so that means I'm going to need to take this and divide by 3,600 seconds. And so I'm going to have 1 over 3,600. And so doing that calculation, 60 miles per hour times 1609 meters per mile times 1 over 3,600 hours per second gives me 26.817 meters per second. Now I'm going to have to do this with 55 miles an hour as well. So let's just do that real quick. Same conversion factors. And that gives me 24.582 meters per second. So I've calculated 55 and 60 miles per hour here. And do note, hours cancel with hours, miles cancel with miles, and I was left with meters per second in my units. Likewise, hours cancels hours, miles cancels miles, left with meters per second. So 26.817. Now, the astute student is going to say, but you only have 2 significant digits there. That is absolutely right. This number is 27 meters per second to correct significant figures. But you want to keep all of your digits until you're done with the problem and then apply your significant digits. Now, since we did it, let's put in the speed of 55. That was 24.582 meters per second. Now I need to calculate the acceleration going from 0 to 60. Well, acceleration is change in speed over change in time. So that's going to be the final speed, 26.817 meters per second minus the initial speed of 0. You don't need units for a 0. Divided by the change in time, which is 2.2 seconds. So you put that in the calculator and you find that that gives us an acceleration of 12.189 meters per second squared. Now, my kinematic equation for position is the first one that I wrote. And so my initial position, 0. My initial speed, 0 multiplied by time. Who cares? It's still 0. Plus 1/2 my acceleration, 12.189 meters per second squared, multiplied by time squared. Now those zeros, obviously carrying those zeros is a little annoying. And so I am going to drop those out and of course divide 12.189 by 2. 9 was not the last digit, so it turns out when you divide that by 2, you get 6.095 multiplied by time squared. And actually, let's put 47 there just so I keep the same number of digits. So there's my equation for the position of car B as a function of time. Now for car A, it's going to constant speed of 24.582. Constant speed means acceleration is 0. So the kinematic equation for this one is going to be initial position 0 plus 20, that's not a 2, 24.582 meters per second multiplied by my time plus 1/2 acceleration is 0 times squared. Well, obviously the zeros again are just a little annoying, so let's just put what matters. 4.582 meters per second multiplied by time. Now I'm just going to set those two equations equal to each other. So XA at time final equals XB at time final, which means that 24.582 meters per second multiplied by time final is equal to 6.0947 meters per second squared multiplied by time final squared. Don't have to be a genius to say, hey, I could divide both sides by time final, and that's going to make my life easier. But then I want to get time final by itself, so I have to divide everything by what time final is multiplied by. So I divide everything by 6.0947 meters per second squared. And that gives me time final equals, put that in the calculator, 4.0333 seconds. So my time here, 4.0333. How many significant digits do I have? 2. So that's just going to be 4.0. But I put all the digits here, and at the end, I will just put a box around what is, well, actually, I can do that right now. Here's what's significant, the 4.0. Of course, you would have to round, but that rounded down, so not a problem. Now, it tells me, okay, now that we found the time, let's put that into one of the equations and then put it in the other one to double check. So putting into the equations, I'm going to have XA at time final is equal to 24.582 meters per second multiplied by 4.0333 seconds equals 99.147 meters. So there's one calculation. XB at time final equals 6.0947 meters per second squared times 4.0333 seconds squared equals 99.147 meters again. So they both agree 99.147 meters. Once again, how many significant digits? 2. Rounding, that's 99 meters. Final calculation. What's the final speed? VB is equal to V initial plus AT is equal to 0 plus 12.189 meters per second squared times 4.0333 seconds equals, and that gives us 46.164 meters per second. And then it says to convert that to miles per hour. So 46.164 meters per second multiplied by the same conversion factors as before, except for I'm flipping them because I'm getting back to miles an hour. So I had meters on top, I need meters on bottom, miles on top. And then I had seconds on bottom, so I need seconds on top, hours on bottom. And it turns out that gives me 110 miles per hour. Now, in terms of significant digits, that 46 was what was significant, and the 110 looks suspicious, doesn't it? Well, it actually makes sense because remember this equation, V average is equal to V initial plus V final over 2. Well, if the two cars are going to have the same distance at the same time, that means they have to have the same average speed, so, or average velocity. So since the car B started at 0, if it's going to average 55, it has to end at 110. It has to end at twice 55 so that Initial plus final divided by 2 gives me 55. So it actually makes perfect sense. So there's a couple problems that should help you getting ready for the exam.